In the last reaction that we saw an ester being converted to an amide. And we saw that we have this alkoxide as our leaving group. Now, that's something that we haven't seen before, and I'd like to take a second and just talk to you about that process and why that happens. So, what we've seen before and we talked about before was SN2. Now, we saw that strong bases such as hydroxide and alkoxides are poor leaving groups for SN1 and SN2 reactions. So the issue and the reason why that is because in this diagram down below, as we look at our reactants coming over to form our products, we can see that our transition state lies somewhere about in the middle. Now the Hammond postulate says that that bond to the methoxide ion is about half broken. Right, so this is going to become our ion as we have our leaving group leave. So it's about half there and about half broken. And because of that, it results in a reaction rate that's sensitive to the nature of the leaving group, since it's about a half broken. Right? So the nature of that leaving group matters because you have to travel through this transition state in order to get to your products. When we look at the reaction that we saw on the previous page, and this is it outlined here again. Here we have our tetrahedral intermediate. So here's our Ti. And in that case, that is where our methoxide would leave. But the transition state for this, because this reaction is exothermic, the transition state lies close to that of our intermediates, right? And our intermediate here is this. It's not really a reactant, but it's closer to this side, right, than it is to this side, right? So because of that, the energy of that transition state and also the reaction rate, it's not very sensitive to the nature of the leaving group because our bond here to the methoxide ion in our transition state has just begun to break because it's living closer, right, as far as it's the way it looks, to our intermediate, which is our tetrahedral intermediate. So let's take a look at transesterification. So transesterification occurs when we have an ester and an alcohol in the presence of a strong acid, so we need a strong acid here, to make a new ester. So here we have our original reactant ester with our alcohol, right, to make a new ester and an alcohol over here. Now the reaction can proceed by an acid catalyzed mechanism or by a base catalyzed route. So let's take a look at the mechanism here and we'll put in our arrows. So we'll see what we get here. Reaction is fairly straightforward though. So the first thing that's going to happen here is we're going to grab a hydrogen ion from sulfuric acid, for example. And we're going to grab it with our carbonyl oxygen. Okay, so that's going to give us an O connected to our H with a positive charge on it and a lone pair, just like so. Now, we'll make a note here that this also has two resonance structures. I'll leave it up to you to draw those out. Now, the next step of this reaction has our alcohol coming over, attacking our carbon. Right. When we do that, we're going to get an oxygen with a plus charge right here, right? And then we're going to take the alcohol and we're going to do a deprotonation. So we're going to come around and grab a hold of that H atom. So that'll give us this ester hydrate. Now we've seen this thing before back in our last chapter, right? Now we're going to come over and we're going to grab another H. Okay, so as we do that, we'll get a formal charge on that oxygen there. Okay. And then what's going to happen next is we're going to take a set of electrons from up here, right? And then we're going to kick off that. So that's what's going to be lost, this group right here. That'll be methanol there, right? That'll give us a positive charge on this intermediate, and then we're going to use one of the alcohols to come over and grab a hold of that H, and that'll give us our neutral product here, right? So in the end, we end up getting a different ester. So notice here that CH3, R group, has been replaced with the R prime group. All right, now, what about base catalyzed? Well, base catalyzed is fairly straightforward. All we're going to do is take our RO minus, right, with the electrons. We're going to swing around and grab a hold of that carbon and do this. So that will give us our tetrahedral intermediate here. And then we're going to swing these down just like so. And we're going to kick off our OCH3. So the other product that we get here is CH3O minus. Right now, as far as the leaving group in this second step, it's true that that could leave. But if so, we would just go backwards. And this is a reversible reaction, right? So the expulsion of that as our leaving group gives us a different product. So that's what we're going to do on our last step there. So the hydrolysis of carboxylic acids follows that same general reaction pattern as we saw before. It turns out that acid halides are more reactive than anhydrous. We saw that, right? Acid chlorides, they're not stable in water. In fact, when we work with them, you have to be very careful that you don't have water present on your glassware. Even moisture in the air can cause a reaction to occur when they're exposed to just the atmosphere. So if we look down below at the reaction of water with an acid chloride, water will come around and attack that carbon just like an alcohol would, right? If that was an ROH, this is the same first step as that, right? So that'll give us here CH3, carbon with an oxygen and lone pair on it, chlorine, and then down here an OH2 plus. Right, now that is your tetrahedral intermediate. So there's your Ti. That oxygen is going to want to come back down and form that double bond and kick off chlorine here. So that'll give you CH3, C double bond O, and then your O, H2 plus. Right? And then you have, in that reaction, you have your chloride hanging out there. So then chloride's going to come over and grab a hold of that, or we could use water here too. In the end, we end up getting our CH3 carbonyl OH there. Right, so you get your hydrolyzed acid chloride. Now the hydrolysis of anhydrides turns out to work kind of the same way. So we come over and we're going to take our water and we're going to grab a hold of one of those carbons. So that'll give us our carbonyl, and then our carbon here with that oxygen, right? Your ethyl up here, and then there's your water with a plus charge on it. So that's your tetrahedral intermediate. It's going to swing down. That'll give us the carbonyl back, right? And then we're going to kick off this group right here. So that will give us our ETO minus. I'm going to take this ethyl and swing it down. So here's our ethyl down here. There's your carbonyl, and there's your OH2 plus. All right, now the last step of that reaction is that we're going to grab one of those H's. You can use water here. You could use, if you wanted to, this also. We're just going to grab one though, so we're going to do this. That'll give us our ethyl, our carbonyl, and your OH, just like so. And there you have your anhydride hydrolyzed. So the hydrolysis of esters is actually just the reverse reaction of the Fischer esterification. Right, so what we're going to have here is H plus. Now that comes from H3O plus because we want to have dilute sulfuric acid here, right? So you're going to have water present in that solution. So as we've seen before, the first step will be protonation of our carbonyl of the ester. So that'll give us a positive charge here, right, with our lone pairs up here. And then we're going to have a lot of water present. We want that present to help drive that equilibrium over to our hydrolysis. Right? Remember, our low concentration of water pulls us to the ester side. A lot of water drives through Le Chatelier's principle, the equilibrium over to the carboxylic acid. Right, so we're going to swing over here, and that's going to give us this. And then we'll do a deprotonation with either ethanol or with water there. So water being in ample supply. Now, what that will do is that will give us this kind of hydrate intermediate. Right, and then we will protonate the ETO group. That'll put a plus charge here on our oxygen. And then we're going to swing down a set of electrons here, just like so. Right? And then over here to our oxygen to give us almost our final product that then gets deprotonated with ethanol or water. Now that last step we'll use either water or alcohol to do your deprotonation. So here we get our final product plus, really, you have ethanol present in that solution too.